So let's continue with this morning session. The second speaker is Takashi Imamura from Chiba University, who will continue from the end of the previous talk and speak about skew column RSK dynamics and the box-ball system.
Thank you very much. So first of all, I'd like to thank the organizers for giving me this opportunity. So yeah, it's my second time to come to India. The first time was in 2004, also in Bangalore. So yeah, I'd like to thank again the organizer for bringing me to India again after 20 years. Okay, so today, my talk is about the continuation of the previous Tomohiro's talk. So in previous talks, Tomohiro talked about our recent project, so Skew RSK dynamics. So my talk is about more a recent topic, Skew column RSK dynamics, which is a certain variant of the Skew RSK dynamics, and its relation to the single species box and ball system. So this is a joint work with Matteo Mucciconi from National University of Singapore and Tomohiro Satsumoto from Institute of Science Tokyo. And so about our talk, so Travis Scrimshaw, joined our project. So first, let me briefly recall the bijection introduced by Tomohiro, and introduce our main result in my talk. So in this paper, and in the previous talk, we have this bijection. So where P and Q is the pair of skew tableau with the same shape. And on the right-hand side, so B1 and B2 is a vertically strict tableau. So this is the example. So we, in VST, so we do not apply any order in the horizontal direction, but we apply the strictly increasing order in vertical direction. And kappa here is a certain certain sequence of integers, and the nu is a partition. So in this talk, we discuss a variant of this bijection, with the following replacement. So this BST is replaced by the HWT, which is called a horizontally weak tableau, which is a kind of dual of the BST. So this is the example. So in this case, we do not apply any order in the vertical direction, but we apply the non-decreasing order, weakly increasing order in the horizontal direction like this. This is the example. This is HWT, and and this K mu, is replaced by K tilde mu. So because we consider a certain dual version of the original dual skew RSK dynamics, so this mu1 is replaced by the L of mu, the length of partition mu here, and the mu prime is replaced by mu I here. So anyway, so under this replacement, so we get another bijection like this. This is the main result. So the left-hand side is the same. Okay. The pair of skew tableau with the same shape, but the right-hand side is a pair of HWT times certain integer of sequence and partition. And this bijection has a certain preserving properties. The first one is the weight preserving properties, which is already introduced by Tomohiro. And we have the length preserving property like this. So in the BST case, so this length preserving property is a relation about the lambda 1, but in this case, because we consider a certain dual version, so the lambda 1 is replaced by the L of lambda. So and sorry, so this d of h is the energy of the function. Which corresponds to the function h in Tomohiro's talk. So before explaining, okay, the purpose of this talk is to explain how to get this bijection. So before, so stating this, so we would like to introduce some notation and notion of tableau. So this is a Skew semi-standard tableau. Yes. And in my talk, we write this tableau as this form. So we remove the frame, and the empty box is expressed as a 0 element like this. So but in order to make the dynamics invertible, we introduce a generalized tableau. So where there are infinitely many 0 elements in the negative side like this, and so in the top row here, so we write the column coordinate marked in blue. Like here. So to this semi-standard tableau, we assign the generalized tableau like this. So by just adding the infinitely many 0 element in the negative side like this. And in generalized tableau, so we also consider this kind of tableau. So the positive element can lie in the negative side, negative column coordinates like this. And we can also define the shape of this tableau by just putting the column coordinates of the rightmost positive element for each row. So in this case, the shape is labeled by the signature. So the signature is a kind of partition, but in this case, the element can take a negative value. So we use the same notation. So as a set of generalized tableau is the shape like this. Okay. So and in addition, we introduce more tableau. So about the pair of generalized tableau. So in my talk, we mainly consider some special pair of generalized tableau of the same shape called the squeezed pair. But this is already introduced by Tomohiro. So I just briefly introduced this tableau. The squeezed pair is obtained by squeezing. So in the VST case, so the squeezing is done in horizontal direction like this. But in our case, the squeezing is done in vertical direction. So we press the pair of tableau in vertical direction, keeping the semi-standard nature. So this squeezing can be done column by column from right to left, like this. And so for example, like here. So first we focus on the fourth column here. And we try to go up the element. So keeping the semi-standard nature. So in this case, we can go up by one side like this. And we also record the 0 element which is removed by the squeezing. So repeating this procedure from right to left, so we get this one. And so this object after squeezing is called a squeezed pair. And we also get a signature. And so this means that any pair of generalized tableau can be decomposed by the squeezed pair and signature. So now, we introduce a certain dynamics, certain time evolution of this squeezed pair. So the building block is the column internal insertion, which is the column version of the internal insertion introduced by Tomohiro. So so first I explained what it is. So this acts on the single tableau, skew tableau, generalized tableau like this. So let me explain this by the particular example. The action of C of 2 of this tableau P. Okay. This 2 is so labeled as a column coordinate. So in this case, we focus on the second column. We start to focus on the second column. Yes? And we pick up the top positive element. In this case, this red 1 element. We focus on this element, and we replace it with a 0 element like this. And this red element bumped out to the next column here. So, and this element bumped out the smallest element. So among the elements, which is equal to or greater than this element. Okay. So in this case, this red element is this element bumped out to this element, and this red 1 element bumped out to the next one. So repeating this procedure, so we finally get this one, and this is the action of C of 2 on P. So this is the column internal insertions, and we also define the iota 2. But the iota 2 is already introduced in Tomohiro.
So, sorry, I'm a bit confused by the dynamics. Could you go back, please?
Sorry?
Could you go back? So when the red one gets bumped, no, in the second one, this one, why does it not go to the next row?
This is a column version. So it goes to the next column.
It goes to the next column. Oh, it's a column insertion.
Column insertion, yes.
Okay. Because the other rows are constant. Okay, thanks.
Yeah. Okay. So iota 2 is so basically the same as the iota 2 introduced by Tomohiro. The only difference is that so we use a column bumping, so a column internal insertion. So for P tableau, this. Okay. So sorry, so we omit the explanation, but this is the example. Yes. And column RSK map can be defined in completely parallel way. So as the usual skew RSK map, it is just defined by the n times the iteration of the iota 2. This is the example. So by using this CRSK map, so we consider the time evolution. Oh, so sorry. Yeah, there is important properties of the CRSK map. So if P and Q is a squeezed pair, which I explained previously, so we see that its image is also a squeezed pair. So its action. So the CRSK of PQ is also a squeezed pair. So that's why. So afterwards we consider only the action of CRSK on squeezed pair. So now we consider the column RSK dynamics, which is the time evolution of the CRS by the CRSK map. So the PT and QT, the T is a time variable, which can take negative, defined by this one, like this. So for the purpose of the application to the Cauchy identity, so we assume that in the initial state P0 and Q0, all the positive elements rise in the positive region. So anyway, we consider the time evolution of the CRSK dynamics. So this is the example of the the column RSK, skew column RSK dynamics. This is the example. And we can see the solitonic behavior. So because when time t is small enough or large enough in a negative direction, so in this case, time t equal -2 and -1, Okay, so dynamics is linear. So this means that so this one, the block of the consequent positive elements like this, so move linearly like this and like this. So and its speed is equal to the length of the blocks. But t is small enough, in this case here. So this object, something collide and scattering happens. But surprisingly, so this 3, 2, 1 structure, the length 3, length 2, and length 1 structure, so recovered when t is sufficiently large, and they move so linearly. Okay. So this is so this is already appeared in the usual Skew RSK dynamics, but it also appeared in the box and ball system. It is very similar to the box and ball system. So in my talk, so this is the goal of my talk. So in my talk, so we connect these Skew column RSK dynamics with the box and ball system. So I think all of you know what so the single species case. In my talk, we consider single species case. So all of you already know the rules of the box and ball system. So because it's probably in the last week, so Professor Tsujimoto introduced this in the lecture. But so we briefly recall the notion and the one properties of this single species box and ball system. It is introduced by Takashi and Satsuma, 1990. And so there are several survey and review papers. So I am learning the box and ball system from this review by Inoue-san, Kuniba-san, and Takagi-san. It is a discrete time deterministic dynamical system of particles on one-dimensional lattice Z. So the state space can be expressed by the binary string on Z. So this is the set of the state space. And in my talk, so we consider the case where there are only finite particles in Z. On Z. And this T infinity is the operator of the one-time update of the state of BBS. So this is update all particles in order from left to right. So the particle chosen, so in this case, so leftmost particle is a particle at -4, moves to the closest empty site, in this case, -1, like this. So these procedures, so repeating this procedure, so until the rightmost particle, so until the update of the rightmost particle finished, so we get a one-time update like this. So and we also consider the time evolution of the BBS like this, and so in this case, so as in the case of the CRSK dynamics. So we also assume that in the initial state B0, all particles rise in the positive region like this. Something the region where the positive column coordinates. Okay. So and it has been known that the linearization. So the BBS dynamics can be linearized by the KKR bijection. So the KKR bijection, so in the SL2 case, the KKR bijection is a bijection between the space of the state of the BBS and a certain pair called the Licht configuration. And the mu is the partition, and the J is some sequence of integers. having a condition depending on the mu. And yeah, Professors Kuniba, Okado, Sakamoto, Takagi, and Yamada shows that this BBS is linearized by the KKR. So yeah, so this situation is summarized as this commutative diagram. So where the T, yeah, this is the time evolution of the BBS. And this T hat is just defined by this one. So keeping mu unchanged, and J is just changes to the J plus mu. So the time evolution of J is completely linear. So, okay. So this is an example of the linearization of the dynamics. So this is the BBS dynamics. So the whole dynamics is non-linear, but this time the dynamics of rigging is linear. So in this sense, so the BBS is linearized by the rigged configuration. Okay. So
sorry,
now, sorry.
I didn't understand what kind of object is J, because you write J plus mu, but they don't seem to be of the same kind.
Yeah. So first, J. So the number of elements in J is L over mu. So in this case, so mu is this one. So the length of mu is 3. Okay. So in this case, there are 3 elements. So J plus mu means that So here, so we add 3. This, and here we add 2. Here we add 1. Okay. So now, I want to state our main result. The main result is as follows. So this is this is a column RSK dynamics. The column RSK dynamics can be decomposed into 2 parts. The first part is a pair of HWTs, and the second part is a BBS dynamics. So the meaning of this equality is that so we have explicit combinatorial algorithms, and according to this algorithm, so the pair of each time. So for example, the pair of this pair can be mapped to the pair of HWT plus the BBS state in the corresponding time, like here. So so as you said, the BBS dynamics can be linearized by the KKR bijection. So this can be rewritten as this form. It's a pair of HW. So this is decomposed into the pair of HWT plus the dynamics of J. So basically, the KKR bijection. So from the KKR bijection, we get a mu and J. But so according to our algorithm, mu is already appeared in the shape of the HWT. So we can omit mu, only J here. So this means this dynamics is J is completely linear. So this means that the column RSK dynamics is linearized by through the KKR bijection. So this is the main point of our talk. And from this bijection, so the bijection which I explained in the previous slide follows as a corollary. Okay, so in the remaining 30 minutes, I want to explain how we get this one. So first, we note that the BBS dynamics is equivalent to the column RSK dynamics for the special pair for n equal 1. So here, the m and n is the number of alphabets in P and Q. So n equal m equal 1 means that the choice of the alphabet is only 1. So in this case, so P and Q should be equal, T like this. Okay, so So here after we just write T in place of T, yeah, the pair TT. And the equivalence of the dynamics is summarized as this diagram. So this is the CRSK dynamics of T. And this is the BBS dynamics. And this one, this is the projection operators. So meaning that so for example, in the fourth row like this, so because there is no positive, so no one element, so this it becomes 0. On the other hand, so here in the fifth column, so there is a one element here, so we just put 1 like this. So the projection is of course not a bijection for general pair of the generalized tableau, but so if you restrict the action on the squeeze tableau, so one can see that it becomes a bijection. So in this sense, so these two dynamics is equivalent. So okay. So our theorems can be rephrased as follows. So the CRSK dynamics is decomposed by pair of HWT and so pair of some special CRSK dynamics of TT. So the tableau having only one element like this. Okay. So so we consider the leading map. The meaning of a leading map is that so starting from a general pair of generalized tableau with the same shape PQ, and so we construct a map from this to some special tableau of TT. So we can do that. So we do this by using a affine crystal structure. So by embedding a affine crystal structure in the pair PQ. So this is our strategy. But so before embedding directly the affine crystal structure in PQ, we first focus on the affine crystal structures on the horizontally weak tableau. But this is the same as the case of the verticalist BST case. So we can equip a crystal structure on HWT by identifying the HWT with an element of tensor product of KR Kirillov-Reshetikhin crystal of SLN with single rows. Okay. So this is the identification. So just lining up the rows like this. This one. So we get the element of the KR crystal with single rows. And for this element, for these elements, we consider the Kashiwara operator, the classical one and the zeroth Kashiwara operator, by using a certain combinatorial rule called the signature rule. So sorry, so I want to also omit the detail of this rule. And also, so we can define and compute the energy D, which is the intrinsic energy. So this can be computed by the combinatorial algorithm by Nakayashiki and Yamada. And the affine crystal structure can be expressed by the certain graph called the crystal graph like this. So where each vertex corresponds to each element of the crystal, and the action of the Kashiwara operators is expressed as edge, the directed edge. So it's labeled I. So first, let us focus on the classically connected component of this graph. So this is the example. The classically connected component is the subgraph of the crystal graph connected by the classical Kashiwara operators, so without zeroth operator. So in this case, the graph is disconnected like this. There are 8 classically connected component in this example. Yeah. So sorry, so yeah, one cannot see the the element. Yeah. So we use also something abbreviated notation. So yeah, we abbreviate this classically connected component as this form. This is the highest weight element corresponding to this element. So this is the lowest weight element here. So the highest element so have no E0, no E1 and E2 arrow coming from this, and the lowest weight element has no F1 and F2 element coming from this. So in this example, so we can draw this type, this picture like this, and this figure, and there is an important property that all elements in each classically connected component have a common energy. Okay, so one can categorize the classically connected component by the energy like this. So this is the example. Okay, so now we consider the leading map of the HWT. So we call the highest weight element here of the highest energy. So the B max. Okay. So so in this figure, so the F0 arrow. So we don't write. I don't write the F0 arrows. But so some of F0 arrow so connect the component with a different classically connected component and a different energy. So the problem is that starting from any element, starting from any element, so we wonder whether we can go to the B max following the Kashiwara operators, including zeros Kashiwara operators. This is the question. Okay. But so this question is related to the connectivity of the crystal graph. But so it can be shown that it has been known that the crystal graph itself is connected, okay, so including the zeros arrow. So this is by something, the very general result of the crystal by Akasaka and Kashiwara. But unfortunately, so in principle, so we can go to the V max from any element by following the zeros Kashiwara operators. But it's not sufficient. It's not sufficient for our purpose. So in order to make a good bijection, having a weight preserving property, so we need a special path to B max, only using a E0 or F0 arrows, which increase the energy exactly by 1. This is the problem of leading map. So this problem is, so in my understanding, not so trivial. So in our previous paper, so Tomohiro talked about. So so we can use the result of the Schilling-Tingley. So we show that the de Majeur zero arrows realize such paths. So for the case of BST, so for the case of tensor product of AR crystal with single columns. But in our case, the tensor product of single rows, so unfortunately, we cannot apply the result of the Schilling-Tingley. Okay. So we decide to try to make something a handmade theorem by using only a combinatorial rule such as a signature rule and a Nakayashiki Yamada rule. So we get these kind of things. Okay. So this is these ones are the classically connected components. So first, so we focus on the the lowest weight element in this case. So for example, so we focus on this lowest weight element. And so we consider the elements. So where so we subtract some constant from this, from all element in this area, the lowest weight element. So such that so some minimal element becomes 1. So in this case, so we subtract 1 from all elements. So and we get this element. So we see that so this element. So we can see that this element is also included in the same classically connected component. And furthermore, so we can show that so this element have a E0 arrows, and so energy increase exactly by 1. So E0 arrows. So by using these arrows, so we can go to the B max from any element of the crystal. So this is the this is the result. Oh, sorry, I skip things. Okay. So this is the reading map of the Kashiwara. The reading map of the HWT. So by using this, so we consider the reading map of the pair of skew tableau PQ. So in order to do this, we first introduce the Kashiwara operators acting on the squeezed pair. So we introduce these operators like this. So acting on the pair, acting on the squeezed pair. So and the classic and in this case, so we label so each E and F has a label 1 and 2 like this, and E1 and F1. So when J is larger than 0, so so the action of this operator is exactly the same as the HWTs. Okay, so so E1 case or F1 case, so change so only change P tableau and act trivially on Q tableau. So this operator does not change Q tableau. Okay? On the other hand, so the E2 and F2, so change Q tableau and act trivially on P tableau. So and as Tomohiro introduced, so we also introduced the zero Kashiwara operators, E10, F10, and E20 and F10, like this form, by using iota 1 and iota 2. Okay. So for these operators, so we have a very nice properties called a crystal symmetry, this relation. So all Kashiwara operators like this, so commute with the CRSK map like this. Okay, so this is very nice properties. So because, so from the crystal symmetry, so we see the following commutative diagram like this. Here, this one. This is a time evolution of a Skew RSK, so Skew RSK dynamics. And also, this is also the time evolution of another Skew RSK, Skew column RSK dynamics. And this C is, at this stage, this C is any composition, so any combination, any composition of the Kashiwara operators like this. So, so from the crystal symmetry, so one can easily see that these ones. So C is, C is any composition of Kashiwara operators. So our strategy is that we choose this C in a way that the BBS dynamics or the equivalent, so that the dynamics of the TT is realized here. Okay? So this is our strategy. Okay? So our strategy is that, so strategy is the following. So okay, yeah. So if t, this one, so time t is large enough, okay, so the p and q, the time evolution of p and q is completely linear. The system is, in some sense, stable. So in this, the stable pair, okay, like, yeah, so like this pair, so we can see that the action of E0 and F0 is the actor in the, yeah, is something completely same way in the case of the, yeah, the small f and e for the HWT case. Okay, so for example, so let's compare the two stable pair like this. So yeah, let's compare the action of F0 like this to the stable pair PQ with the action of the small f0 of the H like this. So this H is it's called the asymptotic tableau of P. So which is obtained by just by lining up the positive element like this. So this is the action of F. So the action of F0. So consists of the promotion operator and F1 operators like this. So and on the other hand, so the action of F0, the capital F0 consisting of iota 1 and the capital F1 like this. So comparing this and column by column, so we can see that for the following things, for positive elements, so in the stable pair, so this one, so iota 1 inverse acts in the same way as this operator, the promotion operator like this. So here in the promotion operator, so this 1 2 2 2 3 2 change it 2 3 3 1 3 3. Yeah, the same thing happened here 2 3 3 1 3 3 and so on. So this means
that you say PR is promotion. Is this the same promotion as in Schutzenberger's?
Yes, I think so. Yeah, promotion. Yeah, it's the same.
But how do you start from the top left corner and then do promotion?
Okay.
How do you, what is?
Oh no, sorry.
So you're just adding 1 to every element cyclically? Is that what you're doing? Okay.
Okay, so sorry.
Okay, thanks.
Okay. Yeah. So at least, as T is so large enough, okay, so the action of the capital casual operator is in some sense equivalent to the action of the small casual operators acting on the asymptotic tableau. So this means that so we can construct a leading map in this way. So where H1 and H2 is the HWT, which is the asymptotic tableau of P and Q. So and from this asymptotic tableau, so we can construct the leading map like this. So which is denoted by L of H1 and L of H2. So then we make the capital L of H1 and the L of H2. This is obtained by just replacing small casual operators by the capital one like this. And then we define the leading map like in this form like here. So so by using this, yeah, so we can establish the leading map at least, yeah, from the stable pair, at least in the stable pair here in the bottom ones. But we know that this is sufficient because we have a crystal symmetry, so, and yeah, so this operation is the same as this operation. So that's why. So this construction is the answer. Okay. So we get okay. So the result like this between the squeezed pair and the pair of HWT and the state of the BBS like this. So yeah. So this one. But there are several equivalent expression of the bijection. The first one is the is something a minimal one. Okay. And so as I said, the square. Yeah. So any pair of the generalized tableau, can be decomposed by the squeezed pair and the partition like this. By using this, so we get this bijection, where the left-hand side becomes not a squeezed pair, but a general pair of the generalized tableau. And we put nu here. And so we further using a KKR bijection for B. So B can be replaced by the leading J. And as I already said, so the KKR bijection is basically the bijection between B and the leaked configuration mu and J, but mu is already appeared as a shape of H1 and H2. So we omit J, omit mu, and we just put J here. And for technical reason, so this J is changed to J plus mu like this. This is kappa. So and the final expression is the expression that I present in the first slide. So this is the most convenient form for the application of the Cauchy identity. So now I want to I want to briefly mention about so the weight and the length preserving property. Okay? So this bijection has a nice properties. So first one is the weight preserving property like this. Okay? Where the volume of nu is so internal shape of the P and Q, and is equal to the energy of H and this one. So to show this preserving property, so we use so we use some two important things. The first one is that so in the right hand side, the energy is included in the right hand side like this. This means that so energy itself is not seem to be related to the volume of rho. So it is something combinatorial object. So this energy is a certain crystal object. So we want to connect this D, the crystal object, with a certain combinatorial object. But also, to see this, so we consider the following fact. When E0 and so E0, the small E0 increase the energy by 1. So this is the properties of the leading map. And on the other hand, the capital E0, so increase the internal shape by 1. So this type of correspondence has been an essential role to connect the energy and the combinatorial object. So the second one is about this one, K. So this K comes from rigging like this, rigging here. The rigging is also does not seem to be related to the combinatorial object. so we have to, so yeah. So, okay, so rather than rigging, the BBS state itself seems to be related to the law. Yeah, seem to be related to the internal shape law. So we want to connect the rigging and the state of the BBS. Oh, sorry. So we know that there is a nice formula about the Kuniba and Sakamoto Yamada, which is the explicit formula for BBS state in terms of a rigging. By using this, so using these properties, so we can get this weight preserving property like this. And the length preserving properties are rather trivial. Sorry. Yeah. So I quickly explain this, and yeah. So by using this bijection, so we have a restricted Cauchy sum. But in this case, not a Q Whittaker, but some modified whole Littlewood polynomial appeared like this. And so this is the result of the restricted Cauchy sum. This, and equivalently, so this is the relation about the length of the certain probability measure for the modified whole Littlewood measure and the periodic Schur measure. Okay, so it is a summary. So yeah, so we obtain a bijection like this. Okay? So behind this bijection, so there is a fact that the CRSK dynamics can be decomposed by the pair of HWTs and the single species BBS dynamics. So and as an application, so we get this type of restricted Cauchy identity or the identity between the probability measure. So thank you for your kind attention.
Thank you very much. Any questions for Imamura-san? Yes, please.
Yes. So are you saying that did you construct a new crystal structure or not? So
the
maybe
crystal structure itself is the usual crystal structures of the Kirillov-Reshetkin crystal.
But
the question is that some certain connectivity of the crystal graph.
Yes.
When we restrict the E0 and F0 arrow on some special E0 and F0 arrow, which increase the energy by 1.
Yes, but is that action E0 a new one?
Yes.
Or
this action is
maybe I'm wondering if you already have action of E0 or F0 for this kind of crystal.
Sorry, I don't understand the question.
So I didn't understand why you had to introduce a kind of action of E0, which
F0 is also okay, but
yes.
we just choose choose E0.
Usually,
but the point is that so we only consider the E0 or F0.
Yes.
Which increase the energy exactly by 1. So for our purpose, we need this type of arrow.
Do we have any choice of E0 or F0 in this structure?
Yeah, so if this E0 and F0 increase the energy by 1, we can choose any of E0 and F0 alone with this, as long as we have these conditions.
I see. Maybe we should discuss later.
Okay, sorry. Yeah.
It's very complicated.
Other question?
I was wondering if there are to which probabilistic models the identity that you establish can be applied.
This one.
Yes.
Yeah. So the modified whole little measure. Yeah. So yes, and so this is has been studied in recent context in KPZ side. Okay, so and basically, at first, so the modified whole little polynomial, it can be obtained by the whole little polynomial with certain specialization. So the geometric progression. So and so the modified whole little measure can be obtained by the whole little measure with such type of geometric progressions. And the stochastic vertex model, the higher spin stochastic vertex model with something with fusion. So which is in some sense described by this type of whole little polynomial with geometric progression has been studied by Buffetov and Matteo and Petrov, and also Agarwal, Borodin, and Wheeler. And in Agarwal, Borodin, and Wheeler paper, so they used the modified whole by further applying something a Plancherel specialization. So they get a PNG type model. It's certain generalization of the PNG type model.
All right, so in the interest of time, I suggest that you keep any further question for the lunch break, and let's thank Imamura-san again.
Thank you.